Hey everyone, welcome to The Explainer. I am absolutely thrilled to have you here with us today. Just take a second and look around you. The buildings we work in, the cars we drive, the bridges we commute across, our entire modern world is literally held together by joined metal. But, how often do we actually stop and think about the intense physics, the incredible geometry, and the rigorous testing that goes into every single one of those microscopic seams? Well, today we are going to take a fascinating journey through the entire life cycle of a weld. We're going to explore the raw power it takes to melt solid steel, the precise ways we fit it together, the hidden enemies that threaten structural integrity, and, my favorite part, the ingenious ways we actually hunt those enemies down. Okay, let's dive into this. Here is our roadmap for today. Number 1, the spark of creation. 2, putting it together. 3, the conflict. And 4, the resolution. All right, let's kick things off with Section 1, the spark of creation core welding processes. So to manipulate solid metal, you need immense power and, quite frankly, unbelievable heat. We aren't just gluing things together here, right? We are fundamentally changing the state of the material from solid to liquid and then back again. Our first stop is shielded metal arc welding, or SMAW. A lot of folks just call it stick welding. The welder uses an electrode that's basically a core wire coated in flux. When that electric arc strikes, it generates intense heat. Now notice how that flux coating burns? That actually creates a gaseous shield that protects the molten metal from the atmosphere. And at the same time, it forms a liquid slag that floats right over the weld pool, deoxidizing it and protecting it as it cools back down into solid metal. Now, the real beauty of SMAW lies in its rugged versatility. The equipment is simple, it's inexpensive, and it's highly portable. And because that protective shield is generated by burning flux right at the arc, it's incredibly resistant to wind and drafts. That makes it absolutely perfect for outdoor on-site construction. But, it does come with a trade-off. The deposition rate is on the slower side, and remember that protective slag we just talked about? Well, once it solidifies, it hardens into this tough crust over the weld bead, and that requires some pretty labor-intensive chipping and cleaning before the job is officially done. Now, submerged arc welding, or SAW, completely flips the script. Instead of a flux-coated stick, we're using a bare solid wire electrode. So you might be wondering, where's the protective shield? Well, it's literally dumped on top. As you can see, the electric arc is completely buried under this thick blanket of granular flux that's fed from a hopper. Because the arc is totally submerged, there is zero smoke, zero fumes, and absolutely no blinding flash of light. In fact, a welder doesn't even need to wear heavy protective clothing for this specific process. It's kind of wild. By hiding the arc and trapping all that intense heat, SAW achieves incredibly high deposition rates and really deep penetration. This makes it super efficient for thick materials. But, of course, there is a direct cause and effect limitation here. Because you're relying on a loose blanket of granular powder to cover a pool of liquid metal, well, you are completely at the mercy of gravity. So this immense speed and efficiency come at the cost of positioning. SAW is strictly limited to flat or horizontal welds. Plus, the welder can't even see the weld puddle as it forms. Next up is gas metal arc welding, often called MIG welding. Notice that continuous solid wire electrode right in the center? That wire is fed automatically through the welding gun by a machine. Instead of relying on a burning flux coating or a big pile of powder, this process uses an externally supplied gas, like argon or a gas mixture, and pumps it straight through the nozzle to shield the arc. Because that wire feeds continuously, it completely eliminates all the downtime of having to stop and swap out burnt electrode sticks. That vastly speeds up the whole operation. This method is a real game changer when it comes to versatility. It works in all positions, and there's no slag to clean up afterward. That means way less waste and much lower downtime. But we have to contrast that efficiency with its vulnerabilities. Remember how stick welding was so great outdoors? Yeah, GMAW is the exact opposite. Because it relies on a cloud of external gas being pumped through a nozzle, just a simple draft of wind can blow that protective shield right away. That exposes the molten metal to the air and totally ruins the weld. Plus, dragging around those heavy gas cylinders definitely makes the equipment a lot less portable. Moving right along to Section 2, putting it together, types of weld joints. So we understand the physics of how we melt the metal, but how do the actual pieces fit together in the first place? Well, the orientation of the pieces determines the joint type. The 5 most common configurations are the butt joint, where plates sit edge to edge on the exact same plane, the lap joint, where pieces literally just overlap each other, the corner joint, bringing perpendicular edges together,
the edge joint, where parallel plates are welded along their shared edge, and finally the T-joint, where one plate is placed perpendicular against the flat surface of another, forming a T-shape.
And this brilliantly illustrates what those definitions actually mean in practice. See how a butt joint creates a single continuous flat surface? Now notice the lap joint. This one is incredibly common when you're joining pieces of differing thicknesses, mostly because they just rest right on top of each other. And if you look at the T and corner joints, those are usually secured using what's called a fillet weld. A fillet weld is incredibly economical and adaptable because it doesn't require complex edge preparation before you start melting the metal.
All right, let's get into Section 3, the conflict, common welding defects.
As much as we strive for absolute perfection, welding is inherently a chaotic process. Physics, contamination, and even just plain human error are constantly conspiring against a good weld. The first major enemy we face is porosity. I want you to imagine a microscopic bubble of air trapped in a freezing ice cube. That is exactly what is happening here, but, with molten steel. As the metal cools and solidifies, trapped gases are frantically trying to escape. If they can't get out in time, they leave permanent cavities inside or right on the surface of the weld. This is typically caused by moisture, a dirty base metal, or a contaminated wire. It can be scattered all over, clustered up, or form in a straight line, but make no mistake, it always weakens the joint.
Next up is the undercut. Now, unlike porosity, which is an internal bubble, an undercut is a physical scar right on the outside of the metal. It basically looks like a groove gouged into the parent metal right along the edge, or what we call the toe of the weld, and it's left completely unfilled by the filler material. It usually happens when the rapid solidification of the metal prevents it from wetting back properly into the groove it just melted.
But hey, for every technical failure, there is a specific engineered prevention. So why does an undercut actually happen? Well, usually it's a direct consequence of using way too much heat, meaning the amperage is just too high or the welder is moving the electrode too quickly. The prevention here is strict parameter control. A welder simply must decrease their arc travel speed, lower the arc voltage, or adjust their torch angle to give that molten metal the time it needs to fill that gouge before it freezes solid.
So, we know that surface scars like undercuts are visible to the naked eye. But what about subsurface porosity? What about those microscopic cracks hiding deep inside the metal? If just a single internal flaw can literally bring down a skyscraper or a bridge, how in the world do we find an enemy we can't even see? That brings us to our final chapter, Section 4, the resolution, rigorous weld testing. Let's play detective. Broadly speaking, testing is divided into two categories. First, we have destructive testing, which is exactly what it sounds like. We take a sample piece and we intentionally destroy it. We might snap it in a tensile test to measure its ultimate yield strength, or bend it until it folds to check for ductility and root penetration. But obviously, we can't destroy an entire bridge just to see if it's strong enough. And that's where non-destructive testing, or NDT, comes in. This is the high-tech wizardry used to check a finished weld without damaging the final product. The most primary and economical non-destructive method is visual testing. But of course, it's restricted to what the human eye can actually see. To enhance this, we use liquid penetrant testing. And honestly, this is essentially magic through physics. A brightly colored, really thin liquid dye is applied to the metal. Through capillary action, that liquid naturally seeps down into microscopic, invisible surface cracks. After wiping the surface clean, a chalky developer is applied on top. That developer actually reverses the capillary action. It sucks the dye back out of the crack, creating a bright, highly visible bleed out against a contrasting background. Pretty brilliant, right? Now, if the material is ferromagnetic, like most steel, we can step things up to magnetic particle testing. The physics here are absolutely fascinating. The inspector induces a powerful magnetic field directly into the welded part. If there is a hidden flaw or crack sitting just below the surface, it literally interrupts that magnetic field, causing what's called flux leakage. When magnetic particles are dusted over the surface, they are magnetically grabbed and held in place right over the invisible crack, acting as a bright red flag for the inspector. But what if the flaw is hiding deep in the center of a super thick steel beam? For that, we use radiographic testing. This is identical in concept to getting a medical X-ray for a broken bone. Short wavelength electromagnetic radiation is blasted straight through the metal onto a photographic film on the other side. Because an internal pocket of air or trapped slag is far less dense than solid steel, it actually allows more radiation to pass through. That leaves a dark shadow on the resulting radiograph, perfectly revealing the exact size and shape of any internal porosity. Finally, we have ultrasonic testing. Instead of radiation, UT shoots high-frequency sound waves, way above human hearing, straight through solid steel. Because the speed of sound propagation in a specific material is constant, the machine can time exactly how long it takes for the sound wave to bounce off the back wall of the metal and return to the sensor. If the sound wave hits a hidden crack halfway through, it bounces back too early. By mapping these echoes, inspectors can trace the hidden internal geometry of the metal with incredible, almost unbelievable precision.
So, we've traveled from the 10,000-degree spark of a shielded arc down to the geometry of overlapping plates, through the microscopic bubbles of trapped gas, and finally into the high-frequency sound waves keeping us all safe. It is a world of immense power tamed by incredibly precise engineering. Knowing the invisible chaos of heat, the constant threat of hidden flaws, and the rigorous science used to find them, how will you look at the welded steel structures holding your world together differently tomorrow? Thank you so much for joining me for this explainer. Keep asking questions and keep learning.